discuss about the search agent. So this is the first part, yeah, about the search agent, because of this searching agent, yeah, or searching techniques are very important in intelligent system. Yeah, this is a common thing actually. Yeah, in AI, in IS. Yeah. So please find this book. Yeah, you can refer to the first meeting, introduction, and the content, the second chapter here, problem solving. Yeah. Introduction and intelligent agent finish. Yeah, then we go for this chapter, yeah, problem solving, especially section 3 here. Yeah, section 3 about solving problems by searching. Okay, here, this one. So please read for a while, then I will come back, yeah, after 15 or 20 minutes. All right?
Yes, sir.
Okay, please. So you can find, I will show you the cover, yeah. So then you can see the title page, this page. This is the title page. You find this book, yeah, in hopefully provided, yeah, in OSET UTB library, right? Okay. Do you get this one? Was it this book in your library, e-library? Any of you? Did you get?
Yes, sir.
Did you get full access for this book?
Yes.
Okay, good. Yeah, great. So then please download this book, and because of most of the contents are taken from this book, yeah, this textbook. Yeah. Third edition or fourth edition, because there is a new one is actually the fourth edition, 2020. Yeah.
I'm using the third edition.
Third edition. All right. Okay. So the content actually from this part, yeah. So I will show you. Okay, right, this one, and also mixed with the other references, yeah. But majority from this part, the problem solving. Yeah, the second chapter here. And yes, first chapter already done. And now for this, the second chapter from this book, yeah. In our side, today is the third lecture, yeah, about the solving problems by searching. Yeah, so we talk about the search agents, yeah, or searching agents, and example of the problems and the real application, yeah, some real application and solution, how to construct the solution, you know, for the given problems. And also we will learn about uninformed search strategies, yeah, informed search strategies, as well as heuristic function. Yeah. So these are some section, yeah, or topic that we will learn today and the next coming week, yeah, or, yeah, about 3 weeks or 4 weeks. All right. So we go back to the slide. Okay. Okay, so can you see the slide?
Yes,
Yes,
sir.
sir.
Okay, good. Right, so we divide it into 3 or 4 parts, agent, yeah. So the first one is, and this is the first part, yeah, for such agent. So the objectives of this topic, yeah, or this chapter, actually student should be able to define the concept of solving problems by searching, yeah, and describe the concept of state and such state space. And also students should be able to formulate real problems, yeah, as such problems, and describe and apply different blind search strategies. Yeah, the first one is breadth first search, yeah, or BFS, and the second one is depth first search, yeah, or DFS. So this will be covered in the first part, yeah. But if it is not enough time, then we will take some part of this lecture will be proceed or will be delivered on the next the lecture for the fourth lecture. And okay, so what is the search? I mean, in your opinion, what the things that cross in your mind when we talk about the search? Yeah, your idea about the search. Maybe you have learned before during undergraduate or bachelor degrees, or maybe you have read, yeah, the books, yeah, related to the AI. Yeah, I'm not sure what is your bachelor background. I mean the undergraduate background. But if you were studied about the information technology, computer science, or informatics, AI should be covered before in undergraduate, in bachelor level or bachelor degree. So anyone, maybe you have an idea, or maybe you have read before about the search. What is search in your opinion when you think or you read about the search, and what is your idea about the search? Any of you? Because this is the basic one, the basic thing in AI or intelligent system is about problem solving. Then when we are going to solve the problem, we have to perform the search techniques or search method.
Looking for something.
Yes, yeah, that is the basic thing. Yeah, looking for something, or yeah, we can say we are going to maybe to find or conceptually or methodologically, yeah, something like that. So finding the things, yeah, or looking for something, that is the basic one. That is the idea, actually, the searching. Yeah. So when we are going to solve the problems, yeah, of course, at the beginning, because of the problem actually given, right? Okay, the problem is like this, yeah, the scenario, and then with the given problem, you try to find the solution. Yeah, so that's why at the beginning we have to search or to find, yeah, the technique how to solve this kind of problems. Yeah, because there is many such techniques, yeah, in AI. But the things we have to find, yeah, looking for the solution, yeah, for this, yeah, actually the method or the technique how to solve the problems, the given problems. All right, so search is one of the most powerful approaches, yeah, to solve the problem in AI. Yeah, that is the thing. Yeah, so actually it is systematically or methodologically explores the alternatives systematically. So because we use the certain system or method to explore the way to solve the problems, and then find the sequence. That is the point. Finds the sequence or steps. Sequence of the step or step by step to solve or path to solve or to provide the solution. That is the idea of the search. So actually the way of thinking when we are going to tackle or to solve the problem, that is search. So problem space hypothesis, all goal oriented here. Symbolic activities occur in the problem space, and then the search in problem space is claimed to be a completely general method or model of intelligence. That is the problem space hypothesis. Right, so the search agent. So actually search agent is a goal-based agent, that is a problem-solving agent or planning agent. So the agent that provide the problem-solving or planning, and then agents work toward a goal. That is the thing. The characteristic of this agent, for such agent, it works toward a goal, or it works to provide a goal. So that is a state, and that is a goal. And agent, consider the impact of action, on future state, or future states. When the agent work is to identify the action or series of action, of course, to reach the target or to reach the goal. Because we put the initial state, condition, and then we need the action, and there is a goal. And then the agent formalize as a search through the possible solution. So these are some two famous example. This is, for example, in here, the left side, this is a circle. Then you given the problem that you find the way from the initial state here to the target or the goal here. The goal. So the goal is actually to come out from this kind of circle, right? So from the initial state. So you have to search this one, right? What you want, what you have to do, this one, you have to search one by one, right? Manually, we can search one by one, the alternative way. So from here, for example, then we have to go to this place, right? So then searching here, searching which way that available. From here, we have only one available way here. Sorry. I don't know, then immediately appear. Need to, okay. So from here, then you start searching, right? Then this is the only way. The only way is here, right? That is how to find the solution actually. Until this way, then just continue searching, because there will be multiple way actually here. For example, starting from here, there is a multiple way. Whether you follow this way or follow this way. And then start. You have to find, if to go to this way, then stop Yeah, block, go to this way, there is a way, another way here, and go to here and finish, reach the destination. Yeah, that is the search. Right. So from here, if you go to, yeah, because from here, I think not difficult. Yeah. So go to this way, this way, this way, and this way, right? Because all still one way to come out from the circle, right? Here, yeah, and then go to here, go to here. But start from here, we have a two solution, two ways. So if you go to this way, then stuck, right? No way out here. But if you go to this way, then there is the way to down, to come in again to the circle, and then again out to this way, right? And then follow to this way, and then you get the final, or to reach the goal here, the destination. So this is the goal. Yeah, this is the state or initial state. Yeah, we can say. Right. So this is the illustration of the search. Right. So we find or formalize through the possible solution. Formalize the search, and through the possible solution, or provide the possible solution. And there is the 8 queen problems also. So the famous in AI search agent, for such technique here. So later on we will discuss in the next slide about this 8 queen problem. So we have to put the 8 queen, first, second, 1, 2, 3, 4, 5, 6, 7, 8. Then each of these queens will not attack, then will not attack each other, this one. There is no way, because we know how to move the queen, in this case. So the queen will move on the just like this, left, right, and up, down, and also the diagonal, right? Diagonal. If black, and if in on the white board here, the white color, so then follow the white color, right? So like this, for example. So the diagonal will follow the white color. Right. So then we search the possibilities, solution or possibilities ways, the possible ways, So the queen will not attack or against each others, right? So we'll discuss this part in detail for the next slide. And what is search? So the basic idea of search, before actually doing something in order to solve the problem, the possible solution will be explored or will be searched. So before we take the necessary action, to solve problem, then we have to find the possible solution. To search or to explore the possible solution. And search is an important approach, to general problem solving purpose, this search. And such techniques are the most important and pervasive general AI programming technique. So it is a very important in AI and the search techniques. And then we can say search equal to the exploration of possibilities, or we can say mental exploration, of possibilities. And when we are doing a decision, we cannot make sure that we have made the best, actually. So until we explore the various possibilities, or various ways. So these are the search, and theoretically the search is this is the definition theoretically. Yeah, search is the systematic examination, yeah, of states to find the path, yeah, from the start, yeah, the initial state, yeah, or root state, yeah, we can say, yeah, as I mentioned in the previous slide, yeah, from the start, yeah, or initial state or root state to the goal state. That is search, yeah. So I mentioned here, yeah, this is start, yeah, or initial state, we can say, yeah, and then this is goal state. So the search is actually, yeah, the systematic examination of states to find the path. Yeah, so we have to search, yeah, which way actually will bring us, yeah, to solve the problems or to get the solution, yeah, the way out, yeah, in this case, yeah. So state find the path, yeah, from the start, yeah, to the goal state, and the set of possible states together with operators, defining connectivity constitute of the search space. And then, yeah, the output of such algorithm is actually a solution. Yeah, so yeah, this is the output. Yeah, so actually when we perform the search means that we find the solution. So the output of such algorithm is solution. Yeah, how to solve this problem. Yeah, so that is apart from the initial state. Yeah, to satisfy or to meet the goal test. Yeah, goal test. All right, so in the real life, search usually result from lack of knowledge. Yeah, sometimes we don't have enough knowledge, and we have to provide the solution. Yeah, in this case, we need to, yeah, because of we have to solve the given problem, yeah, in real life without any knowledge or even without any experience. So that's why sometimes because of the lack of the knowledge, sometimes the solution is not satisfied, yeah, or doesn't meet the requirement, something like that. So in AI, search is merely an offensive instrument which to attack the problems, yeah, that we can seem to solve the better way. Yeah, so search in artificial intelligence, a lot of AI, yeah, many things, yeah, in AI is about search actually. So in many problems, yeah, the sequence of steps are required to solve not known, yeah, it's actually unknown in advance. So we don't have any knowledge, even or with limited knowledge or limited information, but must determine by systematic, yeah, try and error exploration, yeah, of alternative solution. That is the thing. So sometimes we don't know in advance, yeah, or we don't have enough knowledge, yeah, but then we must determine the solution, yeah, or the systematic try and error, yeah, we can say try and error exploration, yeah, or of the alternatives or the way to solve the problems. All right, so search can be applied to many problems. Yeah, these are some examples. Yeah, like the solution to puzzle. Yeah, such as tile games, yeah, the famous one, and crossword. Yeah, yeah, and many I mean the puzzle or the games that can be solved by searching. Yeah, and then also to find the shortest path on the map. Yeah, actually this technique we use, yeah, almost every time when we go and use the Google Map, for example, then actually it is using this the search technique, yeah, in AI. So finding the shortest path on the map. And then proof of a theorem. So in a search method, yeah, in AI, we can use this method or technique to prove a theorem. And also a sequence of moves to win a game. Yeah, it's almost the same with this one. Yeah, the sequence or step by step of moves. Yeah, to solve the problems or to win a game. And the other thing, the sequence of transformation to solve symbolic integration problem. Yeah, and then a sequence of moves to achieve the goal actually, or to reach the goal, or to achieve a desired state, yeah, or the goal state. Right. So these are the classical AI problems that we can solve using the search techniques. Yeah. So like a puzzle, yeah, 8 Queens, a Tower of Hanoi, Missionaries and Cannibals, a water jug, a vacuum board, yeah, a block word, traveling salesperson, yeah, a maze, yeah, crossword, puzzle, arithmetic, wheel of fortune, chess, bridge, yeah, and so on. Many problems that we can solve by using the search technique. So when is search useful? So search is particularly useful for handling or tackling the problems, yeah, for which a direct method is not known, yeah, or not practical. Yeah. So we use a direct method to solve, or direct logical thinking to solve the problem is not practical. So then we use this search, yeah, like a traveling salesperson problem. Yeah. So because of there is a many possible ways, yeah, yeah, then we should find the shortest path, yeah, with the minimum cost, for example. So then we can use this search technique. Yeah, and many real world optimization problems, yeah, like scheduling, the best scheduling, yeah, for the Olympic Games, for example, for robot and navigation, planning movement, yeah, yeah, optimization, yeah, especially for automatic circuit board drills and so on. Yeah, so many real world, yeah, especially for optimization problems. And then in early days of AI, it was thought that searching through possibilities was enough. Yeah, at the beginning, yeah, when AI found, yeah, it was thought that this technique, yeah, searching, yeah, through many possibilities, yeah, was enough, yeah, to solve the given problem, yeah, at that time. So it is interesting domains, yeah. Yeah, for example, chess player, yeah, chess game. So there is many way, with many possibilities, yeah, because of each, yeah, each was a part, yeah, or uh, uh, in each one in chessboard, yeah, we need to find the possible ways, yeah, yeah, according to the kind of the movement, yeah, for each one. So there are too many possibilities actually, yeah, especially in chess player, yeah, chess play or chess game. So we need to search intelligently, yeah, or smart, yeah, evaluate the possibilities, yeah, yeah, even though we don't need to investigate every single possibility, because so it takes time, yeah, of course, yeah, like we play the chess, yeah, we use the like a timer, yeah, so then put the average time, because we cannot, move, yeah, during the player, the chess player, yeah, even sometimes we lose because of the time duration, yeah, we takes too much time when we find the solution, so the people can lose because of the time duration. That's why the constraint in search is sometimes we have to consider the time. That's why we cannot think all the possible ways why one by one, every single possibility. That is the thing. So we have to decide smartly in this case, intelligently, define, and that's why if we have the experience or knowledge, maybe we can find the best in based on the previous experience, the best way to solve problem. Right. So these are some examples of search. So like before deciding on a move, the chess player will consider, as mentioned, a number of possible moves, right? Weighing up the probable benefits of each. So we have considered one by one. If we move to this way, what will happen next? If we move this different way, what will happen next? All the things we have to consider, even though we cannot think every possibility for the single thing, because it takes so much time, so we cannot do that one, but we have to find the best best way based on the what's the experience or our knowledge. That is the way. And when trying to solve the Rubik cube, a person may this is a chess player, is the Rubik cube. A person may try a few moves in their head, so before deciding on the next move, so then we find the possibilities based on the given position of the Rubik cube here. Then we try moves based on what we think, based on what we think. Then we have to see the possibilities and find the way to move. All right, so to solve a maze, this way, I mean this one, we may follow some path which leads to a dead end, it's also similar to the previous case, with the circle one. So, but actually this is the start point, start point here, and this is the finish, the goal. This initial state is the goal. So we find a way how to reach the destination. So from here there is two possibilities. Go to this one or this one. Then there will be a dead end. Means that we trap on this way and then finish. If in the game, in the real game, then it will be finished. So then this one we have two ways again, two options, right? So to this one also we have two different options, and this one also we have a different option. So this one we have two different options again. That is the possibilities. So from this one we have two different options. And then go to this way. Then we reach the destination, finish. That is the search. And the other examples of search, this is about actually about the traveling. In deciding the map, the road. Deciding to travel is the common example from the textbook. Travel in Romania, say from Arad to Bucharest. The capital cities of Romania is Bucharest. So we would look at the different routes on a map before choosing one. So how many possible routes are there? right? So this is the weight, yeah, for each. The weight, we can say maybe cost, yeah, maybe weight, maybe times. It depends on the given parameters actually. Right. So from Arad, yeah, here, from Arad to the Bucharest. So we can see, yeah, from Arad there is how many possible way from Arad here, starting from Arad, right? So from Arad there is a three possible way, right? Through here, and through here. Right? That is the first thing that we have to consider, yeah, because we have to find the possibilities, yeah, to reach Bucharest, right? So that is the thing, yeah. So until in CPU, then we have a different option. Yeah, here only one option. Go to here, and from Craiova we have two different option again. Yeah, yeah. So then we have to find. Yeah, yeah. Depends on the requirement, whether the shortest path or the least cost. Yeah. So then, based on the search, we can solve this kind of problem. And then route finding problem. Yeah. So typically, this is also an example of the real world application. Yeah. Typically, our example of map search. Yeah. Because of, I think you have this experience. Yeah. Many times that you go to the new place. Yeah. Or yeah, not the usual place, and you will use this application, right? Use at least a Google Map, for example, or the other map. Yeah, so map of searching, so where we need to go from the start, yeah, the location to the other location, yeah, using link or transition. Yeah, so yes, this application includes the tools for driving direction in website, yeah, in car system, yeah, and so on. So this is the application. Yeah, I think we all have this application, yeah, in smartphone. So then we usually use this application to find the road, yeah, the way when we find the address, yeah, new address especially. So then we don't know, yeah, the possible way, yeah, or the possible road, yeah, the possibilities to find or to reach this new destination. Yeah. So that is the one real world application. This is very good example actually, because so in the map, so we can see many possible ways. Yeah, yeah. If we want to reach the destination, and even from the map, it is given, you know, the time duration. Yeah, how long that we will reach this destination. Yeah, so from this way maybe 15 minutes, from this way the second way maybe 20 minutes, from the third way maybe 30 minutes. Yeah, so then it is given on the application. Yeah, actually it is using AI, of course, yeah, by using this kind of technique for optimization. And then traveling salesperson problem. Yeah, we find the shortest tour to visit each city exactly once. Yeah, so this is the real world application as well, because of the salesperson. Actually, they should find the fastest way, yeah, with the minimum cost to reach the city or the customer, yeah, the destination. Yeah, because of yeah, it is the policy of the companies. Yeah, yeah, of course, to save the cost, yeah, during the delivery of the product, yeah, the certain product, for example. So this is the traveling salesperson problem. Yeah, I know these problems when I was work in Coca-Cola, yeah, because of there is many salesmen, yeah, the salesperson in Coca-Cola company, yeah, they will send the product every day, yeah, every morning. They have the destination of the outlets, yeah, or the customers need to be reached or need to be visited, yeah, on the certain day, yeah, certain date, especially certain day, because they have a regular schedule actually from Monday until Saturday. So they have to deliver the products to those outlets, yeah, yeah, or customers, yeah, on the certain time. Yeah, of course, from morning maybe they start to work at let's say at 7, yeah, and they start to deliver the product at 8 or 9, yeah, because so they have to load, yeah, to load the truck, yeah, yeah, with the product, yeah, then they have to calculate estimate, so how many products should be loaded, yeah, to the truck, and then after that deliver, then they should estimate, yeah, with this time, yeah, for example 7 hours or 8 hours, all the products, you know, should be delivered during that time. So that is the thing. So that's why the salesman, yeah, or salesperson must find the shortest way, yeah, to visit or to deliver the product, yeah, to reach the customer or outlets. Yeah, that is the thing. And then VLSI layout also. This is about the position of a million of components and connection on a chip to minimize the area or short-term delays. So the objective is actually to put the circuit component on the chip, so as they don't overlap, yeah, and leave space to wiring. Yeah, this is a complex problem, of course, yeah, because of you can see in chip, yeah, like processor, yeah, on the motherboard. If you see the processor on motherboard, then that is actually the complex system, yeah, electronic system, because with many wiring or many connectivities, yeah, from one device or one component to the other components. So yeah, we have to put the circuit component, yeah, on the chip, yeah, yeah, on the board, yeah, so they don't overlap and leave space, yeah, to wiring each other. And robot navigation also, yeah. So this is the real world application, the special case of route finding, yeah, path planning, route finding. So we have to implement the optimization robot with no specific routes or connection, because of there is no predefined scenarios. Yeah, so we don't know actually the way of the robot, yeah, or the route of the robot to reach the destination. Yeah, so the robot navigates, yeah, in 2-dimension or 3-dimension space, where the state space and action space are potentially infinite. Yeah, that is the thing. So that's why in robot we have the method or the technique. It's called SLAM. Yeah, simultaneously localization and mapping. Yeah, so the mapping, in mapping part, yeah, we will find the possible route, yeah, or the possible ways, yeah, to reach the objective or the destination, the final destination. That is the robot navigation. Yeah, we use SLAM usually for autonomous robots. Simultaneously localization, and mapping. Yeah, so mapping is the searching technique we use, yeah, in mapping, because we find the possible ways, yeah, to reach the destination. And automatic assembly sequencing, yeah, also we can see the search in real world application. Yeah, find an order in which to assemble the parts, yeah, of an object, which is in general, this is the difficult and expensive task, yeah, or geometric search. Yeah, so it relates to the automation, optimization. Yeah. Optimization, not only the automation, but we have to perform this task, yeah, to be optimized, yeah, because it relates to the cost of the production, yeah, in companies, yeah, or in manufacturing. So that is the real world application as well. And protein design, yeah, so it finds a sequence of amino acids, yeah, in this case, yeah, that will fall into a 3-dimensional protein with the right properties, yeah, to, for example, to cure some disease. All right, so any question or any comment until this part? Yeah, the real world application of search. No? Aisyah, Martin, Samir, Hasik?
For me, okay, sir.
Okay, all right, good. Yeah, so later if you have any comment or maybe anything that you need to clarify or discuss, yeah, or you want to share your experience also, that is fine, yeah, during this lecture. So talk about the search terminology. So these are some terminologies in search, you know, that we normally use, yeah, during we implement or we apply the search techniques. Yeah, so the first one is a problem space. Yeah, so it is the environment, so related to the environment in which the search take place. That is a problem space. Yes, and or we can say a set of states and set of operators, yeah, to change those states. And then problem instance, yeah, it is initial state or plus goal state. That is a problem instance. Yeah. So the initial state, yeah, up to goal state. Yeah, as I mentioned in the previous slide, yeah, there will be the initial state, yeah, and then, or we can say the start point, yeah, and then the goal state, or the goal or the destination. So the problem instance is initial state plus goal state, and then the problem space graph. It represents the problem state. Yeah, states are shown by nodes and operators are shown by edge. So this is the problem space graph, and depth of a problem. Yeah, it is length of a shortest path, yeah, or shortest sequence. Yeah, shortest path or shortest sequence of operators from initial state, yeah, to goal state. So sorry, I need to confirm. Do you hear my voice?
Yes, sir.
Okay, good. Yeah, because of yeah, I just worry if you don't hear, then I need to again repeat the explanation. Yeah. All right. So the next terminology is a space complexity. So it is the maximum number of nodes that are stored in memory. So this is actually the spatial complexity, and the time complexity. Yeah, the maximum number of nodes that are created. Yeah, and then admissibility. Yeah, it is a property of an algorithm. Yeah, to find or always find an optimal solution. Yeah, and the branching factors. Yeah, so it is the average number of child nodes. Yeah, the branch. Yeah, or child nodes in the problem space graph. Yeah, so later we will discuss or mention in details, yeah, about the definition or terminology of branching factor. And the depth is length of the shortest path from initial state to goal state. That is the depth. So the search problem, yeah, so we can illustrate the search problem here. The search problem is to find a sequence of action, yeah, which transform, yeah, from the initial state to goal state, yeah. Like a G, the form initial, that is the element of G capital. So such problem is represented by a 4 tuple, yeah, here, yeah, with S as 0, yeah, as a set of states, and S0 is element of initial state, yeah, and A is the S operators, yeah, S2 S operators, yeah, or action that transform one state to another state, and G is goal, yeah, a set of states. Yeah, so the goal state, this is action, yeah, so initial state. So these are the space state, yeah, all. And for example, this is the initial state, yeah, the action and the goal state. All right, so the way to find the solution, yeah, or the steps. So we say the search here. So the sequence of action is called a solution plan. Yeah. So it is a path from the initial state to a goal state. Yeah. And then the representation of such problem and such process. Yeah. Such problem is represented using a directed graph. Yeah. So it consists of the states are represented by nodes. Yeah. And then allowed action are represented by arcs. And the generic searching process can be very simply described in the following step here. Yeah. So do until a solution is found or the state space is exhausted. So the first one, yeah, the step, check the current state. Yeah, and then execute the allowable action, yeah, to find the successor states. And pick one of the new states, yeah, that step, and check if the new state is a solution state. Yeah, if the new state is solution, then finish. If not, then again continue. If it is not, the new states become the current state, and the process is repeated. That is the thing. So check the new state. Yeah, if this is the solution, then stop, finish, because so reach the destination or the goal. If not, then the new states will become the current state, yeah, and we will start the process, yeah, again, or the process is repeated. Yeah, that is the way, the generic searching process. So the illustration of the search process, yeah, consider the problem in figure 1 here, yeah. So initial state, yeah, S0, yeah, this one is as a initial state, and the successor states are the adjacent states in the graph, yeah, the adjacent state, yeah, the successor, yeah, or each adjacent state will be the successor. And then there are 3 goal states here, yeah. So this is the 3 goal state, yeah, 1, 2, 3, yeah. So let's say 1, 2, 3, right? So initial state 0, 0. And then the 2 successor states of the initial state are generated. Yeah, so as I'm here, yeah, successor, and the next one, and this one, yeah, will be generated, right? And then the successor of these states are picked and their successor are generated. Yeah, so from this one, yeah, so we find the successor. Okay, there is 2 successor. The one here is stop, finish, yeah, because there is no other link. And then this go to the second successor here, then there will be the 2 successor again, yeah, here. And we'll continue to proceed, yeah, Yeah, then the successor of these states are picked and their successor are generated. Then continue, proceed to the next, and again, if there is the successor, then we continue the next successor, and we repeat the task, yeah, or the process. So successor of all these states are generated. Yeah, so we follow this one. The third process, yeah, is until this and continue with this. Yeah, in this step. Yeah, and then, yeah, the successor of all these states are generated, and the successors are generated here, and a goal state has been found. Yeah, for the first goal here found. So finish the first destination, right? So a goal state has been found. So this example illustrates how we can start from a given state and follow the successor, yeah, and then to be able to find the solution path, yeah, that toward the goal state actually. So we can see the gray node here define the search tree. Yeah, so the search tree, and then usually the search tree is extended one node at a time, yeah, at least. And the order in which the search tree is extended depends on the search strategy. So the order of this one step, yeah, for example, from this one to this one, yeah, that's the next successor, then again, actually depends on the search strategy or search technique. All right, so formulating a search problem. So all such problems can be cast into the following general term. Yeah, this is the how to formulate the search problem. So from the initial state, yeah, and then we have a goal state, right? So at the beginning we have a initial state from the state space, yeah, here from the this one, yeah, state space, yeah, we have an initial state and we have goal state, yeah, here, yeah, in this slide, in slide number 19. Yeah. Slide number 19. Right, then initial state, then goal state. Yeah, we have a goal state. We have in state space, we have an initial state, we have goal states. Yeah, and then we have a permissible operators, yeah, the action that we will find the solution. Yeah. So the initial state is just actually the starting city, yeah, for a route. Yeah, yeah, this is for the traveling salesperson problem. Yeah, for jumble Rubik cube, for example, for a Rubik cube problem. Yeah, that is the initial step, jumble Rubik cube. And the goal state, yeah, or a test for a goal state. Yeah, we can say the destination city for the traveling salesperson. Yeah. And for the Rubik cube, yeah, solve the Rubik cube. That is the goal, yeah, or the destination. Yeah, if we solve, yeah, in Rubik cube should be the same color, all sides, yeah, must be the same color. So that is the solution, yeah, the solution of the Rubik cube. For the traveling salesperson is actually the destination. So which city that we should reach, yeah, as a destination. And the permissible operators, yeah, for the traveling problem, it is a go to city X. That is the operators. And the Rubik cube, yeah, so move actually, yeah, this is movement. And rotate subcube, yeah, for Rubik cube, yeah. So we have to rotate the subcube, so then reach the next aims or destination. Yeah, if this is not the final one, then the process will repeat again. Yeah, will be repeated, yeah, as before, yeah, until we reach the goal. Yeah, that is the operators. So need also to determine the transition model a description of what each action does and what cost, yeah, for especially for the traveling salesperson. And the function that assign a numeric cost, yeah, and then the state and state space, which is the initial state and goal state, are essential in search, and the state, as I mentioned, the state is a state space state. State space is actually the area for that cover the goal state and also the destination state. So the state is one status of the problem, and it captures all relevant information about the problem. The status, like a partial route, unsolved Rubik cube, from starting city to the city, x1, x2, x, and so on, xn and so on. And for the Rubik cube, the unsolved Rubik cube, the orientation of all subcubes of the cube, that's for the Rubik cube problem. And state space is a collection of all states, actually. So all possible status of the problem, also calls search space. It may be finite or infinite. So all possible routes, for traveling salesperson, and all possible combination of subcubes, for the Rubik cube problem. So these are the state and state space. So example in the vacuum world, in the made up vacuum cleaner world, there are only 2 squares. For example here. So there are only 2 squares, and an intelligent vacuum cleaner will perceive which square it is in, or whether there is dirt in the square. So cleaner can choose to move left, move right, set up the dirt, or do nothing. If it is clean, so of course then do nothing. But if it is dirt, then the vacuum need to suck up the dirt part. So the goal is to have no dirt in both squares. That is the thing. So we have to remove this dirt. So then that is the objective or the goal of the vacuum cleaner robot. And state space, there are 8 possible states in the state space here. The first one, the second one, the third one, fourth one, after finish. So these are the initial state, number 1, and number 2, it moves, and clean the part, and back and clean the part, and again, repeat this time until all the things are, all the dirt part are removed. That is the vacuum world state space, right? So we'll repeat all these works, all this state, until the area will be clean. So clean world. So the goal state is state 7 and 8 is one. This is the goal state. The clean world. So the operators are move left, move right, and shut. If there is the part, then it will be shut by the robot vacuum or the vacuum cleaner. And in the initial state is state 5. How to solve this problem? So the solution part, from the initial state to goal state is marked, in red. So then it will be repeated, many times until reach the clean world. All are cleaned properly. All right. So these are the example of cats and mice puzzle. So 3 cats and 3 mice come to a crocodile infested river, and then there is a boat on their side that can be used by 1 or 2 persons. If cats outnumber or the mice at any time, the cats eat mice. If cats outnumber, how can we maintain use the boat to cross the river so that all mice survive? Because we have to maintain the balance between the cats and the mice, because so if the cat's more than the number of the mice, so then the cats will eat mice, and that is the condition or the scenario. Yeah, so another version you can see the cannibal and missionaries as well. So from this link, so how to formulate this as the search problem, or how to represent a state? Yeah, so the initial state, yeah, there is the 3 cats, yeah, 3 mice, yeah, with this the left position, left and right, yeah, because so there is a 2 possible to both, yeah, both in the side that can be used for by 1 or 2 person, yeah. So can the I mean the position, yeah, if the cat's in the left, yeah, and the mice with the right, yeah, and the cat at the right, and the mice will be on the left. So the goal state, yeah, initial state, yeah, move, yeah, from this state, yeah, to this state, yeah, with the composition still the same, yeah. I mean, initial state, this is the mice, this is the sorry, the cat, the mice, yeah, they're from the left side, yeah, it's left side. The left side, it is this is the river, yeah, for example. So we'll use the a boat, yeah, to cross the river, yeah, from left to right side. So we have to maintain the number of the mice, yeah, because of if the cats outnumber, yeah, the mice, then the cats will eat mice, yeah, that is the thing. So the number of cats, yeah, left side on the right, the river, this one, yeah. So then number of mice, yeah, this is the cat, this is mice, yeah, on the left side of the river. So and shows the boat in on which side of the river, yeah, and number of mice on right side of the river, and number of the cat on the right side, yeah. So we move. This is the initial state, yeah, all in the left side, right? And we move, yeah, to the right side of the river, yeah. So let's say this is the river, yeah, the water, and this is the left side, this is right side, this is the flow of the water, river, yeah. And then we have to move to cross this, yeah, from left to side to right, sorry, this is right side, yeah, right side, and then this is river, yeah. So then we have to balance this composition, yeah, the number of cat and the number of mice, yeah. So that is the scenario, yeah, the initial state and the goal state, yeah, for when we illustrate this kind of the problems, the cats and mice puzzle. So operators for C and M problem, yeah, legal move is one which moving up to 2 persons to the opposite banks, yeah. So some possible moves are 3 left, 0 0, or become 2 2 right 1 1, yeah. 2 2, yeah, right 1 1, and 2 3 left 1 0. So will be the possible moves, and applying, because we have to maintain, yeah, to be the same, yeah. So then applying on operator moves, yeah, modifies current state, generate a new one operator, yeah, move from 1 mice 1 cat, yeah, and then 1 mice 1 cat, yeah, vice condition which are both pos, yeah, for left, C left or M left, yeah, cat left or mice left, yeah. So these are the step that we can provide, yeah. The complete set of operators would be this one, yeah, 1 mice 1 cat, yeah, left right, and 1 mice 1 cat in right left, yeah. So 2 cat right left, this is the possible move, yeah, in order to make this balance, right? So this is the possible move, yeah. We create the the diagram, yeah, for this, yeah, the movement, yeah, until we reach the destination, yeah, for the all the mice and cat here. And then the previous slide shows an example of state space search and such process for a solution in the state space. Yeah. So we have the other examples. Maybe give you more or better understanding about this such technique. Yeah. And state space search involves the use of the graph, yeah, to keep track of the relationship between states, and each node of the graph represents a state of the problem, and each arc in the graph represents the application of an operator. Yeah, and the solution is sometimes to the sequence of the operators. So the action and the operators, the action which transform the start state to the goal state. Yeah. And sometimes the actual goal state, like in 8-queen puzzle. So that is a thing. And state space representation. So when defining a problem as state space search, the representation of states is critical. That is the thing. Yeah. So this will be the critical part. And then the representation of state must encapsulate all the relevant information necessary for the action. So to decide then what we should do, yeah, what to do the next. That's why this is for the operators or the actions, and none of the irrelevant information. Yeah. So this is in this case, yeah, CNM, cat and mouse problem position of both is relevant. Yeah, crocodile which way the river is flowing are irrelevant. Yeah. And then the initial state, the goal state, the operators should be considered by the representation. Representation where it depends. The representation depends from problem to problem. Yeah, varies. Will be varied the representation, and then clever representation may reduce the computation. And the smart solution or representation may reduce the computation and memory. All right, so this the remaining part I will explain on the next. Yeah. 8 puzzle problem. So the initial state, yeah, the location of each of the 8 tiles in one of the 9 square here. So because of actually only 8 tiles with the number, yeah, and one is blank. Yeah, so is the start state, and the other one is goal state. So the goal state is we are going to arrange, yeah, arrange the tiles, yeah, according to this number. Yeah, 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. So this the initial state, yeah. Then this is the goal, right? So the operators, yeah, blank moves, yeah, can be, yeah. For example, this is the blank. Yeah, we can move this blank to the left, to the right, to the up, yeah, and down. Yeah, left, right, up, down. Yeah, so means that we move tile number 2 to down, then the blank tile will move to up. Yeah, that is the way to move the blank tile. So goal test, yeah, the state match the goal configuration, and each step costs 1. Yeah, total path cost actually number of step. And these are the 8 puzzle problem, yeah, with the state space for 8 puzzle problem here. So this is the original, yeah, or the initial state. Yeah, initial state is the position. So we are going to construct, yeah, the search, yeah, in order to reach the goal of the state. Yeah, goal state. Goal state will be range, yeah, according to the number, yeah, 1, 2, 3, 4, 5, 6, 7 until 8. Right. So then we have to consider the blank one. So the blue tile here. Yeah, the blue tile. This is the blank tile. So we have a 4 possibilities way. Yeah, 4 possibility way. So to move the blank space. Yeah, the first one, let's say we say the blank space will move to up. Yeah, so then we move down number 4, tile number 4. Then the blank space will be will be up here. Yeah, this is the first one. And then we move the blue tile here, yeah, or blank tile to the left, yeah, to the left. So in this case, we just move tile number 7 to the right, yeah, and the blank tile, yeah, the blue one will be on the left, yeah, right. And then the other possibility to move down, yeah. So we move the blue tile to down. The way to move is we move tile number 8 to up, yeah. So then it will change. So the blue tile or the blank tile will be on, the location will be on the down. Yeah, this is the down side or the survey, this one, and this on the down side here. And then the right, the right side, how to move the blue tile to the right side or blank tile? So we just move 6, yeah, number 6, yeah, tile number 6 to the right, to the left side, sorry. So then the blank tile will be on the right, yeah. So these are the 4 possibility way, yeah, 4 possibilities ways to move the blank tiles. And that is the first node, yeah, after the root. Yeah, this is, we can say this one as parent, the first one, initial state, yeah, as the root. So then we have tiles, yeah, or the node, yeah, with up, left, down, and right. So each node, yeah, each child, also we can create the branch for this. So the possibility of the first one, up here, yeah, the position is up here, yeah, the blank tile or the blue tile, yeah, in on the center, yeah, but then up side, yeah, in the middle of the upside. And then we can move this one, yeah, to the left, yeah, because this one already up, so then we move to the left. Yeah, the position is only left and right because of down, then we'll back to the initial state. So we move the possibility to the different position, yeah. So we don't move to the down again, because of if we move down this one, yeah, number 4, we move to up, then we'll back to the original or initial state. Yeah, so then we will not do that. Yeah, so then the possibility after up, then there is a left and right, yeah, for this blank, this blue tile or blank tile. So for the left, yeah, when we move the left, so means that number 1 we move to the right, yeah. So then we will get this one, left side, right, on the corner, exactly. And then to the right side, yeah, also the same thing. So we move number 3 to the left, then we'll get the right side of the blank tile or blue tiles. Yeah. So because we put the color of blue of the blank tile, right, in order to make it easy. Yeah, to make to see easier. Yeah, if we put the color here, so then we can focus on that side and that part, yeah, that tile. Right. So the first one finish this one, yeah, corner. Then we got this, yeah, position, yeah, but still not the destination. This is not the goal, yeah, because of still we do not reach the goal yet. So we need to expand again, yeah, for the next, in the next position, yeah. These are the first layer, the second layer, and then for the second part, yeah, second leaf here for the second child, yeah, node from the second node from the root, yeah. So we have this position. So we cannot move this one, yeah. Only we move to the right. Sorry, the up and down, up and down. We cannot move to the right, because so we move this position to the right, and it means back to the initial state. Yeah, back to the initial state. So we don't do that. Yeah, we know, we see the other possibilities to move. Yeah, so the possibilities only 2. Yeah, up and down, because so if we move to the right, then we back to the initial state. Yeah, so this one. So then we move up. Yeah, move up. So we will get means that 1, we move 1 to down. So we'll get this position. Yeah, if we move up, and if we move down, yeah, so then number 5 tile we move up, so we'll get this position. right? So still, this one is not the goal, the destination, or the the goal, yeah, the goal of this puzzle problem, yeah, a puzzle problem. So you need to explore again, yeah, to construct the other nodes, yeah, or tile, then again construct the possible moves, yeah, or possible movements of the blank tile or a blue tile. Yeah, right. So the third one, yeah, down, we have this in the middle of the down side, yeah, the blue one, yeah, or blank tile. So the possibility we cannot move up, yeah, down there is no space, yeah, up it will back to the initial state. So it is not possible. So because of we will find the solution. If back to the initial state, then back to the zero, yeah, to the root. Yeah, so we have only the left and right movement, yeah, in order to create different possibilities, yeah, to provide different possibilities. So move to the left, yeah, left side. So means that we move number 5 to the right, yeah. So then we'll get this part, yeah, this position. And if we move to the right, the blue tile, so we have to move number 2 tile to the left. So we'll get this position. Still, it doesn't reach the goal, yeah. So we should again provide the step, yeah, like the previous step, like this step, yeah. So then we need to construct again the the child here, the branch, yeah, in order to reach the goal. All right, so then the last one, number 4, this one, yeah, in the middle of the right side, yeah. So then we cannot move this one to the left side, yeah, because we will back to the original state or the initial state. So we have the possibility only to move up and to move down, yeah, move up here or to move down. So if we move up, so we'll move number 3 to down, and the blank tile or the blue tile will move on the up position. And if we move this one down, so we move number 2 to up, then the the blank space or the blank tile will move, yeah, on the down, yeah, on the down side, yeah, the corner, exactly on the corner. Still, it doesn't reach the goal, yeah. So then we need again to construct for each, yeah, for each. So for this one, yeah, we have the possibility only down, yeah, because of if we move again to right, then we will back to the initial one, yeah. So we have only one position here down, and this one we cannot move to the left, yeah. We have the position only to down again, yeah. So in number 6, so 6 will put on the top, yeah. And then this one also we cannot move to the down, yeah, this one we cannot move to the down because it will come back to the original, to the previous position. So we move only to the right in this part, yeah, right, yeah, up, down, because of left already, right, yeah, this up, left, right, and down, yeah. So that is the things, yeah. And then this is down, yeah. So we cannot move to the up, yeah, because of up already here. So we only move to the right, yeah, because of left already taken. Then up, down, right. This one down, left, right, up. Yeah, we move only to the up position. We cannot move to the left because it will back to the original position. Yeah, this one also the same. Yeah, we cannot move to the left. Yeah, we have to move to the up. Yeah, because if left, then we'll back to the original position. Yeah, so down, left, right, up. Yeah, down, left, right, up. Yeah, so up. This one, up. Yeah, this is down, left, up, down, right. Yeah, right, left, because of left, up, down, and right. This down, left, right, then up. This is right, up, down, then left. That is the way. Yeah. So the possibilities that we have to construct, yeah, If already available means that we will back to the original position, but we do not do that. Yeah, we do the new location, new position in order to construct and to reach the goal. That is the way. So understand this step because this is very important. This is for generic one. Before we go to the BFS and DFS, yeah, breadth, depth first, and also breadth first, yeah, state algorithm, yeah, state, and also depth first, yeah, depth first. All right, breadth first and depth first algorithm. So, any doubt here? Any question? Because this is very important to understand the logic, yeah, the searching. Clear so far? You can imagine this one, this puzzle. Can you hear my voice? Yes, Amir? Clear?
Yes, sir.
Clear? You understand this
Yes.
one? Okay. Yeah, still, because this one is still not the complex one. This is the example, the way to think, yeah, the way to provide I was at the search or the step on the searching technique. Yeah, so still, I mean, not the complex system. Yeah, right. There are many other things that more complex, yeah, for this kind of the search technique. All right, so another example, tic-tac-toe. Yeah, tic-tac-toe is actually the state space representation for this problem is summarized. Yeah, the stage, yeah, you know this game, yeah, is yeah, this is an old one because of many more interesting games, yeah, especially using the graphic, but this one, the traditional games, yeah. So the stage, yeah, the logic, using only the logic. So state is a description of a board that can be occupied by either space, yeah, a node, yeah, or zero or a cross, yeah. And initial state, the blank board, yeah, this is will be the initial state. Then the successor or the successor function or action, yeah, put the symbol in each empty position, yeah, so that there is 3 symbols in the same row, column, or diagonal, a diagonal for each. Yeah, so whether it is zero or cross. Yeah, so yeah, put until it constructs the 3 symbols in the same row, column, or diagonal. And the test support state having 3 same symbols, yeah, in a row, column, or diagonal. So this is the way. Yeah, for example, we put the cross in the middle, so we create this board. Yeah, because the objective or the goal we have to construct with the 3 same symbols. Yeah, whether it is in the row, yeah, column, yeah, or diagonal. Yeah, on the same row, same column, or on the diagonal position. Right. So if we put this one, yeah, there is 3 possibilities to put. Yeah, even actually each one we have many possibilities. Yeah, 8, this one 8. So because of, for example, this one, yeah, the first one on the top row, yeah, the possibilities we have 3 possibilities. Yeah, this one, the top row, 1, 2, 3. Yeah, we can put. So we have 8 because of 1 already occupied, right, by cross symbol. So we have 8 blank space actually. 1, 2, 3, 4, 5, 6, 7, 8. Right. So then we construct 8 possibilities of this symbol. Yeah, yeah, in order to create to make it. I mean, to reach their goal. Yeah. So the first one, the possibility on this side. Yeah. And the second possibility is still on the top row, on the middle. Yeah. In the middle of the top row. And the right side. Yeah. The left side in the middle top row. And then the right side. Yeah. And then this one, the second possible position, yeah, here. Yeah. In the middle of the right side. Yeah, here. Yeah, and then this one, yeah, on the right side of on the bottom side here, yeah, right bottom side here, and then this is the middle of the bottom side, yeah, and then this is on the left side of the we can say bottom or left side, yeah, the bottom of the left side, yeah, you can say also like that, or in the middle of the left side here. So there is 8 possible position, right? So then the next, yeah, we have to determine here, for example, based on this one, yeah. So we put the second turn, yeah, after north, yeah, here the 0 1, the 0. Then we the turn is to cross, yeah. So then, for example, based on the second part here, based on this, so there is a possibility to put the cross, yeah, here, or this part, yeah, or this part, yeah, or this part, or this part, or this part, or this part. Also, there is a 1 2. Sorry, this one no, yeah, this is already given. 1 2 1 2 3 4 5 6 6. Yeah, because of 3 already occupied, right? So 3 space already occupied. So we have only 1, yeah, 2 3 4 5 6. So this one occupied here. Yeah, so actually there is a 7 position, but this one occupied. Yeah, then we put here, and we can move to this side. Yeah, for example, the next one. Yeah, this is the original. Yeah, there is here. Yeah, and then we can put this one middle and this side, and then the next one. Yeah, cross 0 this side, and we can put this side all. Yeah, so then we have many possibilities for this. Right? Okay, so then again, if it doesn't reach the goal, then we have to construct the different possibilities, yeah, the different ways. Right, so until it reach the goal, yeah, the goal of this tic-tac-toe. All right, then the next example is about the 8 queens. Yeah, so 8 queens. So in the 8 queens problem, we need to place 8 queens. Yeah, 8 queens on the chessboard. Yeah, so that no 2 queens are in the same row, column, or diagonal. Yeah, so no 2 queens. Yeah, so because of it will attack each other. So this is the goal. The goal to be like this. Yeah, so no 2 queens are in the same row. Yeah, same row. This is a row. Yeah, or column. Yeah, this is column. This is row, and or diagonal. Yeah, so we check. Yeah, for example, the first queen, check. There is no other queen. Yeah, that cross this row, column, and diagonal. And the second one also. The third one also. The fourth one, 6 1 8. Sorry, 7. Yeah, 1 2 3 4 5 6 7 8. Yeah, 8 queens. So that is the goal. So this is the incorrect solution. Why? Why this is incorrect? Because of these 2 queens. Yeah, these 2 queens are on the same diagonal, isn't it? Yeah, these 2 queens are on the same diagonal. So we have to move this one to different location in order to avoid this kind of situation, right? So that is the goal of 8 queens. So we have to follow this one. Yeah, yeah, by logic using the searching. Yeah, so then one by one we should construct the leaf from the road. Yeah, the original state, yeah, or initial state, yeah, until it reach the goal, yeah, of this game. Yeah, so in 8 queens problem, so the arrange queen on the board so that no queen is attacked by others. Yeah, that is the one. And then the initial state, yeah, any arrangement of 0 to 8 queens on board. Yeah, we have this one. Yeah, for example, this is the initial state. Yeah, not the initial state. This is the right one, the right position. Yeah, you can see there is no 2 queens on the same row or column, yeah, or diagonal. Yeah, you can see, yeah, diagonal. This is diagonal. Oh, this is there is a 1 here. Yeah, you can see which one mistake here. Can you identify from this? Can you see which one mistake or incorrect? The location, which part? You can mention the row.
Diagonal and bottom diagonal.
Yeah, bottom. Yeah, bottom. This one you means?
Yeah.
Yeah, or the top one. Yeah. Okay. So let's say this one. This is the mistake. Yeah, because so it is on the same diagonal, right? From with the top one. Right. So how about the others? Any other mistake from this or incorrect position? Can you see? Any other? The second one, no, yeah. The third one, also no. And the fourth one, also no. And the fifth, no. The fifth, there is a mistake or not? 1, 2, 3, 4, 5. Yeah, we can say this is the 1, 2, 3, 4, 5, 8, 7. Sorry, 6, 7, 8. Okay, so usually we put the number so we can easily to check the row and column. Seven, 8. So 8, 8. Yeah, the 8, 8. Yeah, 8 column, 8 row. Here, yeah, mistake. So only one, right? Isn't it only one or more than one? Can you see? Aisha, Martin, Samir, Asik. This is the basic one. If you can play chess, this is not difficult actually.
Only one.
Only one, right? Okay, good. Only this one. So it should be on which location? Martin, if you can see here, the 8, the mistake one, the error one here, incorrect position, should be on the what position here? Yeah, we use the same column, yeah, because of it should be not on the other column, because we will again another queen. So this is the right column actually, only the row. Yeah, this is the right column, yeah, right one, column number 8, only the row. So which row that we should be put? Yeah, the first row, second row, third row. Yeah, any idea, any comment? This is a logic. In which part? Aisha, Martin, Samir, Hasik. Please comment, please think. Not difficult actually. Or we need to change the location, the position. If this one, because of this one, we put in this one, then we'll against another, right? Put this one also against another. So we have to construct a different position, different location for this. Right. Yeah, we need to construct different location, right? Because of what happen if we put here? Yeah, still against this one. In here also against this one. Here also against this one. So we need to construct different position. Yeah, if we put here, it will against here, right? Put here against here. Yeah, put here against here, put here against here, put here against here, put here against here against here. So we need to rearrange the location. Yeah, I mean the position of the queens, isn't it? So this is the goal. Yeah, this is the right one. This one, right? Because so at the beginning it is the mistake also when we see this one, whether this one or this one mistake. Yeah, if we check this one. Yeah, so we cannot move also in on the other location position because all occupied. So we need to rearrange this all, right? So this is the problem. So we have to solve. Then from this problem, then means that we cannot say this is the incorrect one is not only this one. Yeah, the others we need to rearrange. Yeah. Yeah, because so if we say this is one incorrect, so then we can move to the others, but it is not. So we have to rearrange of this position. Because for here, for example, row number 7 and column 8, yeah, still there is another queen here. If we put here, also another queen. Put here, another queen. Put here, another queen. So cannot. So we have to rearrange for this. Yeah, so this is the goal. Yeah, basically this is the goal. Yeah, so we have to construct, and the queen position should be like this. So with this initial position, initial state, so any arrangement of 0 to 8 queens on board, and then operator add the queen to any square and call test. Yeah, 8 queens on board, none attack, none of the queens attack each other. Yeah. And path cost, yeah, may or may not be applicable or depends on the formulation. Yeah, so this is the formulation 1. Yeah, state any arrangement 0 to 8. Sorry, it's only always appear the request to verify the browser. So the formulation, yeah, so initial state has 64 successors. Yeah, successors. This one, I have problem with this authentication. I don't know. So I mean the network. Yeah. So it always appear the authentication, security authentication. You open the browser, but when I open, it doesn't work. Right, so the second formulation is 1. So any state, yeah, again of 8 queens on the board, and initial state, all queens are at the column. Yeah, this one is initial state. Yeah, yeah. Then we have to construct. Yeah. So any arrangement of k queens in the first k row, such as that none are attacked. Yeah, the initial state, 0 queens on the board, successful function, and the goal test, yeah, none are attacked. And then for the traveling salesperson, yeah, location, cities, yeah, the stage, or even the whole tour, yeah, depends on the problem formulation. Yeah, and then the initial state, yeah, starting points, yeah, and no cities visited. And the successor or operators, yeah, move from one location to another one. Then we'll improve the tour. And goal test, yeah, actually all location visited, yeah, optimal tour found, and agent at the initial location, and the path cost and the distance between the location. And then performing the state space search. Yeah, state space search involves finding a path, yeah, from the initial state of search, yeah, to a goal state in the state space. So we build a search graph, yeah, or search tree, starting from the initial state or the goal state, and we expand the state, yeah, by apply the operators to the state, yeah, and generating all its successor states or functional states. and the successors place in the next level down of the search graph. So then we can see, we can provide the tree search or graph search. The research actually function the tree search, problem strategy, returns a solution or failure. And then loop 2, the problem, and then if the front is empty, then return failure. So then this is the graph search, avoids exploring redundant phase or path. The function graph tree, problem strategy, return the solution, will initiate the frontier using initial state of the problem and initialize the explore to set to be empty. And loop 2, this one the condition, if the frontier is empty, then return failure and choose a leaf node according to strategy. If the node contains a goal state, then return the corresponding solution. Expand the chosen expand the chosen for the choose a leaf node, failure, then only using initial set of problems, I explore set to be. So there is a general search, tree search and graph search. Can you see the slide?
Yes, sir.
Okay.
Yes, sir.
Okay, so these are the general search representation, problem representation using the graph, the left side and the right side using trees. So this is the graph, and the other side is using trees here. The graphs here, trees. So then we can use which one that's suitable for example, for like a PFS and TFS, depth first and search and breadth first search using trees. For TSP, traveling salesperson problems, we can use a graph. So tree terminology. So this is very important when we construct the tree. The trees to solve the problem, especially using search. So we have to know the tree is a hierarchical collection of nodes. In this case, for example, A, B, C, and so on. Right. So actually hierarchical, hierarchy based on the hierarchy, collection of nodes, and nodes are connected through branches. So you can see here, A is the root, or the parents. We can say this is the root or parents. All right. So root, all parents. We can say A, and then we have a branch here or child. So A, we have A here having 1, 2, 3, three branch. So nodes are connected through branches. Right. So there is branch from A to B, A to D and A to G. Right. So 3 branch. And then A is called root. Node, which is also parent. Right. So node also parent of B, D, G. So A is parent or root of a B, D, G. And the maximum number of branches from a node is called branching factor. So you have to know this one. How many branching factor in this case? There is a 3, because of only 3 child, or 3 branch. So there is only B, D, G. So means that from here 1, 2, 3. So means it has only 3 branch. 3 branches. Then we can say branching factor of this tree is 3. Right? Yeah. And the longest path from the root, yeah, from this one, from A, yeah, to the deepest node is called the depth of the tree. Yeah, from the root here, yeah, to the deepest. Which one the deepest? Can you see here the deepest node? Which one? Yeah, which
NF.
N and F. Yes, exactly. N and F. N and F is the deepest, right? So A has 3 branches. Yeah, B, D, G. So we call this one as a branching factor. So 3 branching factor. And for the deepest, yeah, we have N and F. So we count the longest path, yeah, from the root, yeah, from A to N or F, yeah, because N and F are the same level, yeah, the same level here. So the same row, we can say. So we count, yeah, from A, yeah, so D, yeah, E, I, M, N, or M, F. So how many level here? D, E, I, M, F, or M, N? How many? How many? Martin, Samir, Aisha?
5.
5, yes. Yeah, so then the depth of this tree is 5. Yeah, D, this is 1, 2, 3, yeah, 4. Yes, correct. Yeah, 5. Yeah, N or F the same. Yeah, so the depth of this tree is 5. Yeah, the branching factor is 3 because only it has only 3 branches. BDG. So understand until this part because this is very important. Sometimes in the question, exam or test, we ask about this one construct with 3 branching factor or with how many dips and how many depth you have to count, calculate. So for example, the instruction you construct with the 3 branches or branching factor and also the depth until 3 or 4, something like that. So you have to know this kind of what's that the terminology, right? So very important. And then the search strategies, a search strategy is defined by picking the order of node, expansion, and strategies are evaluated along the following dimension. Soundness, these are the way to evaluate, soundness, when a solution is written, and is it guaranteed to be correct or not, and completeness, is the algorithm guaranteed to find a solution, and there is one, and time complexity, how long does it take to find the solution, and then space complexity, how much the memory does it need to perform search, and optimality, if more than one solutions are possible. So does it find a least cost solution? And then the key concept, we want to find the solution while realizing in memory as few as possible of the nodes in state space, which is represented the search tree. So then we can see the time or space complexity here, and time and space complexities are measured in terms of the maximum branching factor of the search tree. So the maximum one. So then we can see here, then maximum depth, for this. So for this one, how many? How is the maximum branching? For this tree, the branching factor, how many? For this tree?
2. 2.
2.
Branching factor.
2.
2? No. Any other? The branching.
3.
3, yes. Because of the branching is like this. This is the branching. Right? So then the maximum depth, we can see how many the depth here.
how many steps?
3.
Yes, 3. Correct.
3.
Yes, 3. So then in order to reach the depth, yeah, the deepest node, so it needs 3 steps, yeah. For example, from 1, go to the branch 6, yeah, then 7, then 8, or 9 or 10, yeah, then it reach the deepest nodes, yeah, or the depth, yeah, the deepest of this in these 3. So that is the maximum depth. So assuming that the path is the least cost solution, so for example in this case, 167, we assume that it is the least cost solution, for d equal to 2. We are often interested in worst case complexity. So this just assumes. Later in the real case, so we put the cost, for each destination. For example, from 1 to 2 there is a 6, for example. 1 to 6 there is a 3. 1 to 2 there is a 5, for example. So then we can count each path, then we find the least cost solution, for to reach the destination from the road node, or from the parents. Right. So the search strategies, there is a uninformed and informed search. Uninformed we can say as a blind search, and informed search we can say we could call as the heuristic search. So in uninformed search, can only distinguish goal and non-goal state, and doesn't use information about number of steps from current state to goal. Basically it doesn't inform. So we don't know the information about the number of the step from the current state to goal. So that is the uninformed. And the informed, we use the guess or estimate how far from the state to the goal in deciding which node to expand next. And it uses the information about the problem to guide the search. So these are in uninformed, it consists of it. This is the family members of uninformed search. I mean, it consists of the breadth first search, BFS, expand shallowest node, and then depth first search, expand the deepest node, so this shallowest, and this is the deepest, DFS and BFS, and the others DLS, depth first with depth limit, and iterative deepening search, IDS, DLS with increasing limit, actually the DLS with increasing limit, and then bidirectional search or BDS, is also search from a goal towards initial state, and uniform cost search or UCS. It is a expand least cost node. So there is a 6 method, or technique under uninformed search or blind search. And under informed search or heuristic search, there is a greedy search, or best first search, and A-star search. So we have a 2 in informed search. All right, so these are the pseudocode of the graph search algorithm. We say the breadth first, and we will learn more about BFS and TFS in this first lecture. So then the algorithm, BFS algorithm, is the least open, is the queue, or FIFO, we can say, first in, first out, and successor are added at the end of the list. And for DFS, depth is if the list open is a stack or LIFO, we can say, last in, first out, and successors are added at the front of the list. So this is the BFS example. So means that the shallowest. So if we have the parent here, the first one, so we'll go to the shallowest. So from A to B, then we finish the B first, and then we go another shallowest, the C. If we have 2 branches, Yeah, from A, we have a branches to B and C. Yeah, for example, and we go to the shallowest. Yeah, B and C. So B and through the C. Yeah, see here, B and C. Yeah, and then back again to B. Yeah, the shallowest. Then we finish. Yeah, we create another branches, D and E. Yeah, so yeah, so A we put A, and then A we have A is closed. Yeah, after we construct the B and C. B and C open. Yeah, A closed means that we cannot. It's already closed. Yeah, with two branches. C B and then B. Yeah, B put we close because we have we create two branches here, D and E. Yeah, so the remaining is D and E, the new one, and C. Yeah, C is still open because C we do not create the new branches. Yeah, for this. And after we create for C here, FG, then we put FG and ED. Yeah, because of C becoming closed. Yeah, here closed. We already created the branches. Yeah, with F and G. Yeah, F and G. So the open only D, E, F, G. Open means we can construct the branch, yeah, from this open node, the open node. If closed means that it is finished. Yeah, it is finished. So we cannot construct the branch of the node. Yeah, for this. This is open and closed. Right. So when we construct the BFS, we go for the shallowest first. Yeah, shallowest. Yeah, the breadth first. That's why the name is breadth. Yeah, we go the broaden area. Yeah, means that the same level or the same. We can say the same row. Yeah, we finish the same row first, and then we go to another row, the bottom, the shallowest row. Yeah, close to the parents or close to the road. So that is the way of the BFS. So the flow will be from here and here and here. Yeah, that is the breadth. Yeah, breadth first search BFS. Yeah, so this is the BFS. So we construct or create the branches. Yeah, for the shallowest first. Yeah, so here A, yeah, BC we create it, and then B create, yeah, BC, yeah, and then we start from the B back to the B, then create the branches, here D and E, and then continue with C, then create the construct the FG, yeah, here, yeah, and then we finish again back to the D, yeah, in order to construct H and I, and back to E, construct J and K, and back to F, yeah, this E and F, construct L and M, yeah, and then after L and M created here, and back to the G, and construct N and O, yeah. So then we'll get this one. It will close, yeah. This if it reach the destination, then we'll close, yeah. As if still like this means open, yeah. This open, this close, is open, still because of the branch is not created yet. Yeah. So then we say this one is still open. Yeah, this one closed, already created the branches. Right. So these are the how to construct the shallowest first or BFS. Yeah, breadth first search. Yeah, the method. So we go to this one. Yeah, the layer by layer. Yeah, layer by layer. Yeah. So finish first, and again the next finish, again the next until reach the destination or the goal. Right. So then the other technique or method is DFS, yeah, depth first search. Yeah. So this example. Yeah. So in depth first search, so we go for the deepest. Yeah, the deepest node. Yeah. It is totally different. Yeah, with BFS, we go to the shallows. Yeah, so the closest to the root. Yeah, but for the depth of first, we go to the longest, yeah, distance to the root first. Yeah, for each branch. So this is the illustration. Yeah, for example, A. Yeah, so from A. Yeah, we construct B. Yeah, yeah, and C, then B, we construct, yeah, we finish, yeah, this B with DE, yeah, so then we close this one, yeah. And then after we close this one, then we construct another, yeah, and we create the branch for another branch, for another node here, and then we already closed and we created this one at the deepest. So then, until this one all finished. So for the deepest, so we go to this one for vertical, like the column, So the column node, based on the column. So if BFS is based on the row, so horizontal. But in DFS we go based on the vertical because of the deepest. So for the same search tree, nodes are explored in order A, B, D, E, C, F, G. So that is a different pattern, because of this is the different technique, to explore. So this is the order for DFS, A, B, D, E, F, E, C, F, G. That is the way, So A, B, D, E, C, F, G. This is the sequence. You have to understand this. This is the sequence of the DFS. It is different with the BFS. BFS A, B, C, D, E, F, G. A, B, C, D, E, F, G. This is exactly like the sequencing of the alphabet. But this one different. A, B, D, E, C, F, G. Right? So that is the difference between BFS and DFS. So this DFS deepest of first. So you have to solve the deepest one. After that, then go to the next. Then after finish the deepest, then you can construct the different branch. With the different node. Then after that, reach the deepest one. Then again construct the different node. So this is the way. So BFS or DFS example. So use traveling in Romania, from Ered to Bucharest as an example here. So for example, Ered, Ered to Bucharest. This is Ered. This is Bucharest. So then the question, how would you present the initial state, final state, operators, and can the full state space be drawn from this? So a state can be represented as a city for simplicity. To the initial state is arrayed. So initial state is arrayed because of the start. The start or the initial state. Or the start point is arrayed. The destination is Bucharest. Here. This is the start. This is goal. Bucharest. So then Arad, with Arad, after expanding Arad, we can see here Arad, there is a 1, 2, 3, 3 branches, right? So Serin, CPU, and Timisoara. Yes, Arad, with CPU, Timisoara, and Serin. So after expanding CPU, this is still the same. The second layer still the same between BFS and DFS. But the others then will different. I mean, the way to solve, the way to solve, or the step to solve to reach the goal will different after this. This is still the same. BFS and DFS still the same. But after expanding CPU, then BFS will expand Timisoara next. After CPU, and with BFS will expand to Timisoara. So the next one. In DFS, you expand to the Arad after CPU. So after CPU here, we'll go to in here in Arad, we go to the Timisoara, the second one. This is for BFS. But in DFS, we go after CPU. Yeah, so here for BFS, the next step after the first branch, yeah, and this one to this branch, we go for DFS, depth first. Yeah, so Arad, yeah, Fagres, yeah, in CPU there is Arad, yeah, there is Fagres, there is Rimnichu Filcia and Oradea, right? So Oradea, yeah, again Arad, Rimnichu Filcia and Fagres. That is for CPU, right? So then we go to this. And then for the BFS, we go to the depth. I'm sorry, the shallowest, not the depth one. So the next one after CPU is Timisoara. So that is the thing. Yeah, so we can see the difference between BFS and DFS. Yeah, for this one. So then evaluation of the search strategy based on the time complexity, how long, the completeness, yeah, whether the strategy is guaranteed to find a solution if one exists, or based on the time complexity, how long it takes to find a solution, space complexity, optimality, yeah, how much memory needed to perform the search, maximum number of nodes, yeah. Optimality also check, yeah. Time and space complexity are measured in terms of the branching factor of the search tree, yeah. Maximum number of child of any node, and shortest step from the root to a solution node, and maximum depth and the state space. Yeah, and these are the properties of BFS. Yeah, we can see the completeness, yes, but if P is finite, but in time complexity, this is how to find the time complexity, space complexity, and optimality, whether it is we can get the optimum or not. Yeah, so still ambiguous for this one. Yeah, for the properties of DFS, optimality is no. Yeah, so it might not find the shortest or optimal path. Yeah, so it is linear for space complexity, and for time complexity is terrible for DFS. It's much larger than D. All right, so we see the weakness of the BFS and DFS here. Yeah, the BFS, as we can see, the depth and nodes, time and memory is one. If depth 2, yeah, so the first one, the 2, then the nodes will be 110. Yeah, for example, if we have B, branching 10, yeah, branching 10, and then node is 1000 bytes, and required time, yeah, processing speed is 1 million nodes per second. Yeah, the branching factor is 10. So there is 10 branches. So if that 2, then the nodes will be 110, and the time will be 0.11 milliseconds. But if we go further, yeah, for example, 16 depth with this same condition, then it will take, yeah, the memory 10 exabyte, and the time to finish 350 years. Yeah, the nodes will be 10 power 16. So it is very long. Yeah. So the memory requirement plus exponential time complexity are biggest handicap of the BFS. That is the things. That is the weakness of the BFS. Yeah. So it takes a long time to solve this problem. Even for 12 depth until 12, then it will solve around the 13 days. Yeah, more than almost 2 weeks to finish this work, this task. Right. So then for DFS, almost the same. Yeah, we call that for BFS with the same branching. Yeah, 10 branching factor, with 1 million nodes and 1000 bytes per node. Then with depth 16, yeah, the node almost the same, and the time to finish 350 years, yeah, with 10 exabytes, still the same. Yeah, so at depth D16, so we go down from 10 exabytes to 156 kilobytes. Yeah, in DFS, this is for the 3 search. Yeah, so still this is not the best solution. Yeah, to find, yeah, to solve the problems, but for the simple things, yeah, we can say this one is quite, appropriate, yeah, to solve the problems. All right, so these are the exercise. So you can construct this one, yeah, implement the data structure and algorithms needed for the CM puzzle. So we just to remind how to construct the data structure and algorithm, yeah, for this one. And this is the exercise, yeah, for the 8 puzzle problem, yeah, given the initial starting state, yeah, and what is the branching factor of this such problem, yeah. So then you should define the goal. Yeah, this is the initial state, right? The goal is to make it sequence, yeah, in order, yeah, with 8 tiles. Yeah, so then it will make 1, 2, 3, 4, 5, 6, 7, 8, yeah, tiles. And then you try to solve this one, yeah, and until what the branching factor to such a problem and to solve, to reach the goal for this. Yeah, using breadth for search, yeah, so the search tree that would be built down to level 2, for example. Yeah, assume level 0 is the root of the tree, for example. And using depth for search, yeah, using PFS, the first one, yeah, and using DFS, yeah, search. So the state of the search tree down the level 3. Stop once you have expanded one node that goes to level 3. Right, so this is the exercise. Yeah, for you can try now, yeah, and then finish next week, yeah, for this exercise. Yeah, or this one, this is for homework, yeah, the exercise for homework. Yeah. You finish this one, and for the next, yeah, I will send this slide, yeah, after this lecture.